Hey folks, I'm going to talk about some examples today, and these will be examples using conservation of energy. And the first examples I'm going to do, there won't be any non-conservative forces, no friction, tension, normal forces, or applied forces doing any work. Those forces will be present, but they won't be doing any work. Okay. I did write a little review here. You're welcome to write that down if you want. But it's stuff we've already talked about. Network. If I have all the work done by all the forces acting on an object, that equals a change in kinetic energy. Work done by any individual force is the integral of F dot dr. Okay. Um, so sometimes we do have to actually integrate that. Work done by a conservative force equals negative a change in potential energy. We talked about that pretty extensively. That negative sign is important. Work done by non-conservative forces leads to changes in mechanical energy. Whoop, that's an error. Let me fix that. There we go. And if you put those three equations together, I've kind of this one, and this one, they lead to our nice conservation of energy equation, which some variation of that you would have talked about last year. Now, additionally, here's my examples. So I've got two for this video. The first one is a very simple one. We're just going to do it algebraically, no numbers. And it's real simple. Let's say we shoot a cannon off a cliff at an angle that I am not giving you. So we don't know the angle. And I want to know what's the impact speed. What's the final speed, the magnitude of the velocity that the cannonball strikes the ground with. Notice I'm not asking for an angle there because I can't answer that, but I can answer that final velocity. Now, if you were going to treat this as a projectile problem, I'd have to give you this angle up here. There'd be no way to do this. But it turns out that we can use conservation of energy to figure out at least what the impact speed of the cannonball is. So when you use conservation of energy in this equation up here, there's a not and there's a final. So you've got to establish where you want your beginning and end position. For this, it makes sense to put the beginning position right as the cannonball leaves the cannon and the end position to be right at the moment, right before the cannonball impacts the ground. While the cannonball's in the air, we're going to ignore air resistance. So the only force acting on it's gravity. And so therefore, there's no non-conservative forces acting. At point A, when the ball leaves the cannon, it's going to have kinetic energy. So there's a K naught. It's at a starting height. Now you get to pick where you want height to be zero. I'm going to call the ground zero height. So it's at because it starts off at a height, there is going to be gravitational potential energy at the beginning. There are no non-conservative forces acting, so that the work term is zero. There is going to be a K final because it's going to impact the ground with the velocity, and it's going to be at ground level, so there's be zero height, so there'll be no potential energy. Also, I didn't include any springs. There's no springs here or anything, so I didn't include spring potential energy in here anywhere. Well, then you sub in your equations. So we got 1/2 mv naught squared plus mgh equals 1/2 mv final squared. The m's drop out, and if you solve for v final, you're going to get v naught squared plus 2gh. Okay. Now at this point, if I then gave you the angle that this ball is launched at, well, then you could find vx. It would just be v naught cosine of theta. And then now that we know the vf, that's your vf we just found. And if we now know vx, you could also find vy, the vertical velocity of the ball, right as the moment it's hitting the ground. So using conservation of energy is actually a nifty way to maybe help you solve projectile motion problems. Our other example is going to be a little more involved. And for this example, I am going to give you guys some numbers, okay? So the other example, and I'm going to draw a picture here, and I'm going to suggest to you that you draw a very large diagram because we are going to mark all over it. So let's say here's the ground, and there's some kind of trampoline or spring, okay? And you have compressed that spring 20 centimeters. Okay, it's a spring or a trampoline or whatever. And let's say the spring constant for that trampoline is 500 newtons per meter. And let's say I put your book on top of that spring, and the mass of that book is 2 kilograms. Okay. So here are the questions that I want to answer. I'm going to let this thing go, and the book's going to go flying in the air, and eventually it will come to a stop somewhere up here, and then it'll start falling back down. So I have a bunch of questions for this. One, what's the max velocity? Okay, what's the max speed the book attains? With what velocity does it leave the spring? Okay, that would be when it's right there. So as it's leaving the spring, what's its velocity? And are these two the same? These first two things. And then what is the maximum height that the book achieves above the initial position? Okay, so what is this height right here? Okay, all right, so when does the book reach a max velocity? Okay, what the most misconcepted answer that people will say is they'll say that these two are the same. They'll say the book reaches its max velocity at the moment it's leaving the spring. And it turns out that that is wrong. Okay, at that point, it turns out the book is already slowing down. Okay, so when do we reach a max velocity? Okay, well, at a max velocity, that means you're no longer accelerating. And if we're no longer accelerating, that means net force is 0. Okay, so where does that occur? So let's draw an FBD of our book while it's being pushed up by the spring. Well, in that case, you have the force of the spring and you have the force of gravity. And when those are equal, okay, that is the spot when the book stops speeding up and begins slowing down. That's when the acceleration is 0. Now, we're just looking at magnitudes here. There's no signs or anything. So we get kx equals mg. So the point at which the book reaches its max velocity, okay, is whatever that value of x is. And for this problem, I want to go ahead and plug the numbers in. So the mass of the book is 2, gravity is 9.8, and the spring constant is 500. And if you plug all those in, you get a small number, 0.0392 meters, or 3.92 centimeters. So on this picture, it would be like right about there. Okay. All right. So that's where the max velocity is going to occur. Okay. So we really have 4 points in this book's motion. We have where it started. I'll make that an A. Okay, so we're going to call that A. We have the place where it reaches its max velocity. That's going to be a B. We have the moment when it leaves the spring. We're going to call that C. And then we have when it reaches its max height. We're going to call that D. So it's really important that you distinguish those 4 locations. Now, the first part of this problem, our max velocity, is actually going to be the most involved, and the rest of them, it turns out, are a little easier. Now, we've got, if we look, we have 2 forces acting on the book. We have springs, and we have a spring, and we have gravity. Those are both conservative forces. There aren't any non-conservative forces. So in our equation here, WNC is going to be 0. The U term, though, it can have 2 different energies. You could have spring potential energy, or you could have gravitational potential energy. But both may exist on either or both sides of the equation. So to figure out the max velocity, which is point B, we're going to go from A to B. Okay. At point A, we don't have any kinetic energy. The spring is compressed, so we have elastic potential energy at A. Now, for as far as gravity goes, you got to make a decision where you want 0 height to be. Well, later on, I want the max height above where it started. So I'm going to call where this thing started 0 height. So in that case, I don't have any gravitational potential energy here. Now, it turns out you could pick any place for 0 height, and the problem will still work, but this is a convenient place. And there, again, we established there's no non-conservative work. At point B, the book is moving, so there's going to be a kinetic energy at B. The spring is still compressed. It's compressed 3.92 centimeters. So you still have elastic potential energy at B. And now we are a height above the starting point, so we have gravitational potential energy at point B. So now we just got to be very careful with our substitutions here. So first I'll write the equations out. So we have 1/2 k xa squared equals, and kinetic energy at B, 1/2 mvb squared. That'll be our max velocity. We have elastic potential energy because the spring is still compressed a little bit, so that's 1/2 k xb squared. And then we have some potential energy, that's mgh, okay? Now here's the next part. We got to be real careful on the numbers we plug in. All right, so we got 1/2 times 500. X is always how far is the spring compressed. So for the spring, X equals 0 right here when it's uncompressed, okay? Well, at the beginning, at point A, we're compressed 20 centimeters, which is 0.2 meters squared, equals 1/2 mass of the book. We're trying to find that v squared. That's our max velocity. I'll call that b still. Plus 1/2 k is 200, or 500, sorry, 500. The spring compression at point B, that's our 3.92 centimeters or 0.0392 meters, and we have to square that. And then plus m, which is 2, g is 9.8. What's our height? Well, our height from here to here is 20 centimeters minus the 3.92 centimeters, which is 17.08 centimeters. I'm sorry, 16.08 centimeters, or 0.1608 meters. That's how high we are above the starting point at that moment. Okay. Now, a note here. This side of the equation, if you plug in chug, you get 10 joules. So that means we're playing with 10 joules of energy. At point B, that 10 joules is split between some kinetic energy, some elastic potential energy, and some gravitational potential energy. But if I add these three things that I've underlined in blue, they have to be equal to 10 total, okay? If you try to do this and you plug all your numbers in, you should get a VB. And here's what I got when I did this. I got I take that back. Sorry, guys. I got 2.542 meters per second. So that's the max speed of the book. Now, by the way, that's not very fast. That's maybe about 5.5 miles an hour or so. But hey, at least it's moving. So that's the hardest part. That's going from A to B. Now, the next thing we asked was, what's the velocity when it leaves the spring? That's at point C there on the drawing. So at this point, you have a choice. You can go from A to C, or you can go from B to C. Either one will give you the correct answer. For me, I'm going to pick A to C because there's just fewer terms to mess around with. So I'm going to go from A to C. Okay. So at point A, all this is exactly the same on the left side of this equation. So we've got our 1/2 k xa squared. At point C, the book is moving, so it's got kinetic energy. The spring is no longer compressed, so there's no spring potential energy. The book does have a height, though. Now it's exactly 20 centimeters over its starting point. So there's going to be a gravitational potential energy at C. So if I put my equations in here, equals 1/2 mv at C squared plus mgh, I have all the numbers except for VC. 1/2 k is 500. XA was 0.2, got to square that, equals 1/2, mass of the book is 2, VC squared, I'm trying to find that, plus M, which is 2, G is 9.8, and the height is 0.2 meters. That's your 20 centimeter height. And if you plug and chug, you're going to get a V at C of, I got 2.466 meters per second. Now notice it's a little less than B. It's not a lot less than B, but it is less than B. The book has already started slowing down. Okay, and it turns out we saved the easiest part for last. If I want to know the max height, that's at point D. We can go from A to D, B to D, or C to D. I'm going to choose A. Okay, because that's going to give us the fewest terms. So if I go from A to D, at point A, we only have spring potential energy. Again, the same thing we had in the last two. At point D, the only kind of energy the book has, because it's at its max height, is gravitational potential energy. So we've got our 1/2 kx squared. It's all this, which is still just 10. Okay, that's going to equal m, which is 2, g is 9.8, and we're just solving for the height. And if you plug and chug, you get a height of 0.51 meters or 51 centimeters. So that's the max height the book reaches above the beginning point. If, by the way, you had gone from either B to D or C to D, you have to be careful. You're going to have heights on both sides of the equation. You'd have gravitational potential energy at both sides of the equation, assuming that we're calling this h equals 0. All right, so that's a fairly complicated problem, a lot of parts. So my overall advice is be very careful in drawing each position out. That's absolutely critical. Labeling things as much as you can, and then doing the math. The math itself ain't so bad, but getting everything set up, that's where you're going to spend your time. I hope that was helpful, and thank you very much.